September 14, 1943. The Volturno River Valley in southern Italy. Lieutenant James Harper of the British Royal Engineers stood knee-deep in cold water at 3:15 in the morning, watching his men wrestle a steel panel into position. The panel measured 10 feet long, weighed 570 pounds, and represented something the German Wehrmacht had declared impossible just 6 months earlier. Harper's company was building a bridge capable of supporting a 40-ton Churchill tank. They'd been working for 90 minutes. The mathematics seemed absurd on paper. Traditional military bridge construction required specialist equipment, custom-fitted components, and engineering expertise accumulated over years of training. The bridges built by Napoleon's armies, by Prussian pioneers, by every military force in modern history, demanded weeks of careful construction. Yet Harper's men, most of them civilians 9 months ago, were assembling a structure that would carry Britain's heaviest armour across a 100-foot gap. They were doing it in darkness. They were doing it while German artillery positions in the hills occasionally lobbed shells toward the crossing site. And they were doing it with components so simple that the instruction manual fit on 3 pages. The bridge taking shape in the Volturno's current wasn't revolutionary because it used exotic materials or radical engineering theory. It was revolutionary because it abandoned every assumption about what military bridging required. No welding torches, no surveying equipment, no calculations performed on site, just identical steel panels, steel pins that dropped through pre-drilled holes, and soldiers who'd practiced the assembly sequence until their hands moved automatically in the dark. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German military observers, the ones who'd been captured during Sicily's campaign and questioned by British intelligence officers, consistently expressed the same bewilderment when shown photographs of Bailey Bridge construction. The speed violated their understanding of structural engineering. More troubling, it violated their assumptions about what British and American forces could accomplish with battlefield logistics. A German pioneer battalion required specialized heavy equipment to build a bridge strong enough for panzer tanks. That equipment needed rail transport, which meant the bridges could only be constructed where rail lines reached the riverbank. The British were building bridges anywhere they wanted, using components carried in ordinary trucks. The strategic implications were profound. Rivers had defined European warfare for centuries, precisely because crossing them was slow and predictable. Defending forces knew they had days, sometimes weeks, to concentrate troops at bridge sites. Attacking forces telegraphed their intentions by the sheer logistics required to bridge a major river. The Meuse River in 1940, the Dnieper River in 1943, the Rhine River looming ahead in 1945, these weren't just geographical features. They were natural fortifications that gave defenders time to prepare, time to reinforce, time to turn river crossings into killing grounds. What Lieutenant Harper was building at 3:15 in the morning changed that equation completely. The Volturno wasn't particularly wide, just 90 feet at this crossing point, but German engineers had demolished every permanent bridge within 15 kilometers. Standard doctrine said British armor would sit idle for 2 weeks while engineers constructed a replacement. Harper's company would finish in another hour. The bridge design came from a man who'd never commanded troops in combat, never witnessed an artillery barrage, and never set foot in Italy. Donald Coleman Bailey was a civil servant in the British War Office, a quiet engineer who spent his days analysing road construction projects and reviewing technical specifications. Before the war, his most notable achievement was designing improved concrete formwork for highway construction. He was methodical, detail-oriented, and utterly uninterested in military glory. In April 1940, while German panzers were smashing through the Ardennes and demonstrating exactly how fast modern warfare could move, Bailey sat in his office at the Military Engineering Experimental Establishment in Christchurch, England, sketching bridge components. He'd been assigned to solve what military engineers called the tactical bridging problem. How do you get heavy vehicles across a gap quickly using equipment that ordinary soldiers can handle? Bailey's insight came from observing what didn't work. Every military bridge system in service required components that were either too heavy for manual handling or too specialised for field assembly. The British Army's standard equipment bridges demanded skilled crews working with surveying instruments, cutting torches, and detailed technical knowledge. If you lost the specialist who understood the stress calculations, the bridge couldn't be built. If you lost one critical component, the entire system became useless. Bailey approached the problem backwards. Instead of designing the strongest possible bridge, he designed the simplest possible component, a lattice panel 10 feet long, 5 feet tall, weighing exactly 570 pounds, light enough for 6 men to carry, strong enough to be load-bearing. The genius was making every panel identical, not similar, identical. Every hole drilled at precisely the same spacing, every dimension manufactured to tolerances measured in 30 seconds of an inch. The panels connected using steel pins 3 inches in diameter that dropped vertically through matching holes. No threads to strip, no bolts to tighten, no measurements, required on site. Line up the holes, drop the pin, move to the next connection. A soldier who couldn't read could assemble a Bailey bridge if someone showed him the sequence once. But Bailey's real breakthrough was modularity. A single panel could support roughly 10 tons distributed across its length. Need to cross a wider gap? Connect more panels end to end. Need to support heavier loads? Stack panels on top of each other, creating a reinforced truss. Stack them side by side to double the width. The same components worked for a 20-foot footbridge or a 200-foot vehicle crossing capable of holding a 40-ton tank. The British Army tested Bailey's prototype in December 1940 at the experimental establishment. The demonstration used 12 soldiers with no prior bridge-building experience. Bailey handed them basic instructions and stepped back. In 2 hours and 45 minutes, they assembled a complete 30-foot bridge. Then Bailey showed the observers what the design could really do. The crew disassembled the bridge, reconfigured the same panels into a double-height truss, and reassembled it as a structure rated for twice the load capacity. Total time, including reconfiguration, 4 hours. The watching officers understood immediately what they were seeing. This wasn't an incremental improvement over existing designs. This was a different category of military equipment entirely. If soldiers could be trained to assemble these bridges rapidly, rivers stopped being obstacles that halted offensives. They became delays measured in hours instead of weeks. Production began in January 1941 at factories across Britain. The panels were stamped from high-tensile steel using dies that could be installed in any facility with basic metal pressing equipment. This wasn't custom fabrication requiring specialist craftsmen. This was mass production. By late 1942, British factories were producing 25,000 panels monthly. The United States, recognizing the design's value, began manufacturing Bailey panels under license. American production reached different scales entirely. By 1944, US factories were stamping out panels at rates that would have seemed fictional to pre-war engineers. The first combat deployment came during Operation Lightfoot, the British offensive at El Alamein in October 1942. 8th Army engineers used Bailey bridges to cross anti-tank ditches and wadis throughout the Western Desert. The bridges that halted Rommel's retreat were assembled in darkness by crews working in sandstorms. German intelligence reports from captured documents expressed consistent confusion about how British forces were maintaining offensive momentum despite having no heavy bridging equipment visible in reconnaissance photographs. The answer was that Bailey bridges didn't look like bridges until they were assembled. The components travelled in ordinary trucks, appeared to reconnaissance aircraft as standard supply vehicles, and could be stockpiled near crossing sites without revealing intentions. A German pioneer company moving bridge-building equipment telegraphed their target from 50 kilometres away. British engineers could assemble surprise crossings because the bridge components were invisible until the moment construction began. Sicily, in July 1943, proved the concept at scale. The island's road network crossed countless ravines and stream beds where Italian engineers had demolished every bridge during their retreat. British and American forces used Bailey bridges to replace 55 destroyed crossings in 3 weeks. Some bridges were small, spanning 15-foot gaps that infantry could have jumped across. Others stretched over 100-foot gorges that would have stopped armor for weeks using traditional construction methods. The speed of replacement changed tactical planning fundamentally. Previously, engineers examined maps and identified river crossings that were feasible to bridge. Feasible meant locations where the banks were stable, the gap wasn't too wide, and the approaches allowed heavy equipment to reach the site. Those limitations meant attacking forces funneled into predictable crossing points that defenders could fortify. Bailey bridges eliminated most of those constraints. The components were light enough to be manhandled down steep approaches. The assembly required no heavy equipment at the bridge site. Engineers could build bridges at locations that defending forces had dismissed as impossible to cross with armor. The tactical flexibility this created was worth more than the bridges themselves. By the time British forces reached the Italian mainland in September 1943, Bailey Bridge construction had become routine enough that Lieutenant Harper could stand in the Volturno at 3:15 in the morning and know with certainty his bridge would be finished by 4:30. The crew wasn't hoping to finish. They weren't rushing to beat a deadline. They were executing a procedure they'd practiced dozens of times. The assembly sequence was choreographed like a factory production line. Team 1 positioned the first panel on the near bank, supported by wooden cribbing that kept it level. Team 2 brought the second panel and connected it to the first using 4 pins, 2 at the top corners, 2 at the bottom. Team 3 added the third panel, while Team 1 started positioning the cross-bracing that connected the top and bottom chords. Team 4 laid the wooden decking across the completed sections. The bridge grew outward from the near bank at a rate of approximately 1 panel every 4 minutes. For a 90-foot crossing requiring 9 panels, the mathematical prediction was 36 minutes for the main structure, plus additional time for the approaches and railings. Harper's company was beating that timeline because every man knew his exact role without requiring orders. German artillery threw occasional harassment fire toward the crossing site, shells that burst in the hills behind them or splashed in the river 50 yards upstream. The fire wasn't particularly accurate, probably a single gun crew working without forward observers. Harper's men didn't stop working. They'd been trained to distinguish between random harassment fire and actual targeting. Random shells meant keep working but stay alert. Actual targeting meant scatter to pre-designated cover positions and wait for the barrage to lift. The Wehrmacht's artillery doctrine in Italy by September 1943 was built around conserving ammunition. German supply lines stretched back through the Alps. Every shell had to be trucked down mountain roads that Allied fighter bombers attacked daily. Random harassment was about psychological pressure, making Allied troops nervous and slowing their work. Concentrated barrages were reserved for targets important enough to justify the ammunition expenditure. Harper knew the Germans were saving their shells for the actual crossing attempt, when British tanks would be funneled onto the bridge approaches and vulnerable to plunging fire from the hills. The bridge itself didn't matter enough to waste ammunition trying to hit it in darkness. This calculation meant his construction crew was safer during assembly than the tank crews would be during the crossing. It was cold comfort, but it was accurate. At 4:07 in the morning, the final panel was pinned into position. The bridge now spanned the Volturno's 90-foot width, supported by timber cribbing on the near bank and a steel abutment that engineers had prefabricated and positioned on the far bank before assembly began. The structure looked impossibly delicate, a lattice of steel that seemed far too thin to support its own weight, much less a 40-ton tank. The load rating calculations were straightforward physics that Bailey had worked out in his original design. Each 10-foot panel had a maximum bending moment capacity based on the steel's tensile strength and the lattice geometry. Connect 9 panels in a single line, and the total supported load was limited by the weakest point, which was always the center where bending stresses peaked. For a single-height Bailey bridge spanning 90 feet, the safe load was approximately 12 tons. But Harper's bridge wasn't single height. His crew had stacked 2 panels vertically at each position, creating what engineers called a double-double configuration. This quadrupled the bending resistance because structural capacity increases with the square of the height. The double-double configuration could safely support 45 tons, which meant a Churchill tank weighing 42 tons could cross with a safety margin of 3 tons. The safety margin mattered because tanks don't distribute their weight evenly. A moving vehicle creates dynamic loads as its suspension compresses and extends. A tank accelerating puts more weight on the rear road wheels. A tank braking shifts weight forward. The 3-ton margin meant the bridge could handle those dynamic variations without approaching failure stress. At 4:23, Harper's men completed the approach ramps and wooden decking. The bridge was rated for traffic. Total construction time, 1 hour and 58 minutes. The bridge had been built faster than German intelligence believed possible, at a location German commanders had dismissed as unsuitable for heavy vehicles by soldiers who'd been civilians the previous year. The first vehicle across was a scout car that tested the bridge's stability at 4:30. The car's 2-ton weight barely depressed the span. At 4:45, a Churchill tank from the North Irish Horse approached the near bank. The tank commander, Captain William Morrison, had been briefed on the bridge's specifications, but remained visibly skeptical about whether a structure assembled in darkness by combat engineers could actually hold his 42-ton vehicle. Morrison's caution was understandable. Tank crews developed strong opinions about bridges after watching Sherman tanks crash through inadequate structures during the Sicily campaign. A Churchill was worth approximately £150,000, represented months of British industrial production, and more importantly, contained 5 men who would die if the bridge collapsed mid-crossing. Harper walked onto the bridge and stood at the centre, directly over the point of maximum stress. He waved Morrison forward. This wasn't bravado, it was a calculated demonstration. If the bridge collapsed under Churchill's weight, it would fail at the centre where Harper was standing. His presence told Morrison and Morrison's crew that the engineer who built the bridge trusted it absolutely. The Churchill rolled onto the approach at 4:47. The bridge's wooden deck transmitted the tank's weight as a deep vibration that Harper felt through his boots. The steel panels flexed slightly, maybe half an inch at the centre, which was well within design parameters. The structure's rigidity came from the triangulated lattice geometry. Each panel was essentially a truss where compression and tension forces balanced out. Adding vertical load increased both compression and tension proportionally, but the geometry prevented buckling. Morrison stopped Churchill at mid-span, probably testing Harper's confidence. 42 tons of stationary load was worse than moving load because it eliminated the dynamic distribution. The bridge creaked slightly as the steel settled under sustained pressure. Harper remained standing 5 feet from the tank's starboard track. After 10 seconds, Morrison engaged the transmission and continued across. Churchill reached the far bank at 4:48. Behind Morrison's tank, 8 more Churchills were queued at the near bank approach. They crossed at 2-minute intervals. The spacing calculated to prevent multiple tanks from being on the bridge simultaneously. By 5:15, 9 tanks had crossed safely. The bridge showed no signs of stress beyond the expected half-inch deflection that recovered when each tank reached the far bank. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What made this crossing strategically significant wasn't the bridge itself, it was what the bridge represented about changing military capabilities. 90 minutes of construction work by a combat engineer company had restored offensive momentum that German commanders expected to be stalled for weeks. The North Irish Horse's tanks were now advancing up the Volturno Valley, while German forces were still repositioning to defend the crossing sites they'd expected British armour to use. This pattern would repeat across Italy throughout the autumn and winter of 1943. German forces demolished bridges as they retreated. British and American engineers replaced them faster than German intelligence believed possible. The Wehrmacht's defensive strategy relied on using rivers as natural obstacles that bought time. Bailey bridges eliminated that time advantage. The engineering principles behind Bailey's design weren't particularly sophisticated. Triangulated trusses had been standard bridge architecture for over a century. What was sophisticated was recognizing that simplicity and standardization could transform tactical capabilities more effectively than technical complexity. A brilliant custom bridge that took 3 weeks to build was less valuable than an adequate standardized bridge that took 2 hours. Military doctrine evolved to incorporate Bailey Bridge capabilities into operational planning. Before 1943, staff officers planning offensives identified river crossings and scheduled weeks for bridge construction. After 1943, river crossings became brief pauses measured in hours. The difference accelerated offensive operations throughout the European theatre. The transformation wasn't limited to British forces. American engineers adopted Bailey bridges enthusiastically after observing their performance in North Africa and Sicily. By the time US forces landed at Normandy in June 1944, Bailey bridge components were standard equipment in every engineer battalion's inventory. The modularity that made Bailey bridges fast to assemble also made them adaptable to unexpected situations. Engineers could build a bridge rated for 20 tons, realize they needed 40-ton capacity, and simply add reinforcing panels without rebuilding from scratch. They could extend a bridge that proved too short by adding panels to one end. They could widen a single-lane bridge into a 2-lane structure by adding panels laterally. This adaptability meant bridges could evolve as tactical needs changed without requiring entirely new construction. A bridge built for supply trucks could be reinforced to carry tanks. A bridge built for one division could be widened to increase traffic flow when a second division needed to cross. The same components solved different problems by rearranging them according to different configurations. The weight savings from eliminating specialized equipment created secondary advantages that weren't immediately obvious. A traditional military bridge required heavy transport vehicles just to move the components to the construction site. Those transport vehicles were targets for enemy aircraft and artillery. They required fuel, maintenance, and drivers. They announced the bridge's location to any observer who spotted them moving toward the river. Bailey components traveled in standard cargo trucks that looked identical to ammunition or ration trucks. The logistics signature was invisible. Enemy reconnaissance aircraft photographing roads behind Allied lines couldn't distinguish bridge components from any other military cargo. This concealment meant engineers could pre-position bridge materials near intended crossing sites without revealing their intentions. The psychological impact on German commanders was documented in captured intelligence reports. Wehrmacht officers consistently underestimated how quickly Allied forces could restore mobility after bridge demolitions. This led to defensive planning that allocated insufficient forces to defend river crossings because German staff assumed they'd have more warning before Allied armor arrived. At Monte Cassino in early 1944, German positions overlooked the Rapido River Valley, where American engineers were building Bailey bridges under direct observation from the heights. German artillery destroyed 3 partially completed bridges, killing dozens of engineers in the process. But American forces kept building. The 4th bridge succeeded because German gunners ran out of ammunition before American engineers ran out of bridge panels. The mathematics of that exchange were brutal but decisive. German artillery had limited shells and couldn't afford to keep firing at empty riverbanks once bridges were destroyed. American factories were producing bridge panels faster than combat operations could consume them. The industrial equation favored the side that could afford to keep trying until they succeeded. This dynamic appeared repeatedly throughout the Italian campaign. German forces would destroy a bridge, confidently expecting days or weeks before it was replaced. Allied engineers would have a Bailey bridge operational the same night. German defensive positions established to control the demolished crossing would wake up to find Allied armor on their side of the river, bypassing positions that were supposed to be secure for weeks. The tactical doctrine for defending river lines had assumed that demolishing bridges created predictable delays. That assumption became obsolete in the face of Bailey bridge capabilities. Defensive planning had to adapt, which meant committing more forces to actively defend river crossings rather than simply denying them through demolition. By the winter of 1943, the strategic impact was measurable. Allied offensives in Italy maintained momentum through terrain where previous military operations would have stalled at every river valley. The advance wasn't fast by later standards, but it was faster than German commanders had planned their withdrawals to accommodate. The time advantage created by rapid bridging accumulated across dozens of river crossings into weeks of operational tempo that the Wehrmacht couldn't match. Donald Bailey's sketches from April 1940 had become a strategic weapon that changed how armies moved. The quiet civil servant who'd never sought glory had designed something more valuable than any particular bridge. He'd designed a system that made bridge construction predictable, standardized, and fast enough to matter in mobile warfare. Lieutenant Harper, standing on Volturno's bank at 5:15 as the last Churchill tank crossed his bridge, probably didn't think about grand strategy or strategic implications. He thought about the fact that his company had built their 14th Bailey Bridge in 6 weeks of combat operations, and they'd finish building their 15th before the month ended. The bridges had become routine. That routine was what changed warfare. The Rhine River crossings of March 1945 represented the culmination of everything Allied engineers had learned about rapid bridge construction over 5 years of war. When American, British, and Canadian forces reached Germany's last major natural barrier, they faced a river that averaged 400 yards wide, flowed with spring melt currents exceeding 6 feet per second, and had every permanent bridge destroyed by Wehrmacht demolition teams following Hitler's direct orders. German military doctrine had always treated the Rhine as the ultimate defensive position. The river was too wide for temporary bridges, too fast for reliable pontoon crossings, and too deep for ford sites. Historical precedent supported German confidence. Napoleon's armies had required weeks to cross the Rhine during the campaigns of 1796 and 1800. Prussian engineers in the Franco-Prussian War of 1870 had needed extensive preparation to bridge the river under unopposed conditions. Wehrmacht commanders in March 1945 expected the Rhine to buy them 6 to 8 weeks of preparation time, while Allied forces laboriously constructed permanent bridges or accumulated enough pontoon equipment for viable crossings. Those weeks would allow Germany to conscript and train additional divisions, relocate forces from the collapsing Eastern Front, and perhaps negotiate a separate peace with Western powers before Soviet forces reached Berlin. The expectation was reasonable based on historical engineering capabilities. It was completely wrong based on what Allied engineering battalions had become by 1945. The transformation that began with Bailey's sketches in 1940 and continued through campaigns in North Africa, Italy, and France had created an engineering force that approached river obstacles with capabilities that German staff planning had failed to account for. On March 7, 1945, American forces captured the Ludendorff Bridge at Remagen through a combination of German demolition failures and extraordinarily courageous action by infantry, who crossed while the bridge was still wired with explosives. The bridge provided the first Allied foothold east of the Rhine, but German artillery and air attacks damaged it severely. When it collapsed on March 17, killing 28 American engineers working on repairs, the bridgehead held 25,000 troops who suddenly had no supply line. The 51st Engineer Combat Battalion had anticipated this possibility. While other units were attempting to save the Ludendorff Bridge, the 51st was already constructing a heavy tactical bridge 500 yards downstream. They were using Bailey Bridge components combined with pneumatic pontoons to create a floating structure capable of supporting 40-ton tanks. The engineering challenge was considerably more complex than the Volturno crossing that Lieutenant Harper's company had executed in Italy 18 months earlier. The Rhine at Remagen was 380 feet wide, more than 4 times the Volturno's span. The current ran at 5 feet per second, creating hydraulic forces that could tear inadequately anchored pontoons loose and send entire bridge sections downstream. And German artillery positions in the Eifel Hills had direct observation of the construction site. The 51st approached the problem with systematic precision that reflected years of accumulated experience. They'd built Bailey bridges across the Ruhr River, the Erft River, and a dozen smaller obstacles during the drive through Germany. Each crossing had refined their procedures slightly. By Remagen, they'd achieved a level of coordination where 40 men functioned essentially as a single organism with 40 pairs of hands. Construction began at 1300 hours on March 8th. The first task was positioning anchor cables upstream and downstream from the intended bridge line. These cables would prevent the pontoons from swinging with the current or developing the sinusoidal oscillation that could tear the structure apart. The anchor points were concrete blocks weighing 3 tons each, cast on the west bank and barged into position before pontoon assembly began. The cable mathematics were straightforward but unforgiving. 5 feet per second of current velocity created approximately 2,000 pounds of lateral force on each pontoon. Multiply by the 32 pontoons required for a 380-foot bridge, and the total lateral load exceeded 60,000 pounds, trying to push the bridge downstream. The anchor cables had to resist that constant force, while allowing enough flexibility to accommodate vertical motion as vehicles crossed. Engineers used 1-inch diameter steel cable rated for 20,000 pounds of working load. The cables were positioned at 45-degree angles from the bridge line to anchor points 60 feet upstream and downstream. This geometry distributed the lateral forces across multiple cables while preventing the bridge from developing excessive movement. Each cable was tensioned to precisely 12,000 pounds using hydraulic jacks and maintained at that tension throughout construction. German artillery began targeting the site at 1400 hours, roughly 1 hour after construction commenced. The first barrage consisted of 6 rounds from what American counter-battery radar identified as a 105mm howitzer positioned approximately 8 kilometers to the east. The shells impacted in a dispersed pattern around the construction site, 1 striking the west bank and throwing mud 50 feet into the air, 2 splashing in the river 60 yards north of the bridge line, 3 overshooting into the town behind the engineers. The fire was harassing rather than precision targeting. German forward observers in the hills couldn't see the actual bridge site clearly enough to call accurate corrections. They knew approximately where the Americans were working but couldn't pinpoint the structure itself through the morning haze and smoke from burning buildings along the riverfront. The 51st's standard operating procedure for artillery harassment was to continue working unless shells began impacting within 50 yards of the immediate construction area with consistent accuracy. Scattered harassing fire meant German gunners were firing, blindly, hoping to slow the work through psychological pressure rather than actual targeting. The crew continued assembling pontoons. Each M2 pneumatic pontoon required 15 minutes to inflate using hand pumps. The pontoons were positioned in the water at 15-foot intervals, connected by Bailey bridge panels that spanned between them. The first panel section was assembled on the west bank, complete with wooden decking, then carefully slid out across the first 2 pontoons until it was supported entirely by flotation. This initial section was critical because it established the bridge's alignment. If the first section was positioned even 2 degrees off the intended centerline, that error would magnify across 380 feet until the far end missed the east bank approach by 15 feet. Engineers used surveying instruments and reference stakes on both banks to ensure the first section was precisely aligned before adding subsequent panels. The bridge grew eastward at approximately 1 panel section every 12 minutes. This rate was slower than construction on solid ground because each section had to be carefully floated into position and connected while bobbing on the river's current. Engineers worked from small boats, positioning panels while the pontoons they were standing on rose and fell with the water. The work required balance, timing, and absolute confidence in the equipment's load ratings. By 1700 hours, 4 hours after construction began, the bridge extended 200 feet from the west bank. German artillery increased in intensity around 1730, suggesting that forward observers had finally gotten accurate range information as the structure became more visible against the water. A shell struck 30 feet from the bridge at 1743, showering engineers with spray and mud but causing no casualties. The 51st's commander, Lieutenant Colonel Harvey Fraser, made the tactical decision to continue construction despite the increasing artillery attention. His calculation was straightforward. German gunners would need at least 20 direct hits to completely destroy the bridge, given the redundancy built into the pontoon spacing. The Wehrmacht didn't have 20 shells to waste on a bridge that would be completed within 2 hours regardless. Stopping construction would only give German artillery more time to range inaccurately. Fraser's logic proved correct. Between 1730 and 1900 hours, German guns fired approximately 40 rounds toward the bridge site. 3 shells impacted within 20 feet of the structure. One struck a pontoon directly, puncturing 3 of its 5 air chambers and causing that section to settle lower in the water. Engineers immediately attached additional pontoons to compensate, a procedure they'd practiced specifically for this contingency. The bridge remained stable throughout. At 1900 hours, with fading daylight making German observation increasingly difficult, the final panel section was positioned. The bridge now spanned the Rhine's full width, connecting the West Bank approach to the East Bank abutment that engineers had constructed 2 days earlier in anticipation of exactly this crossing. Total construction time from first anchor cable to completed span, 6 hours. The bridge was rated for Class 40 loads, meaning vehicles up to 40 tons could cross safely. A Sherman tank weighing 33 tons could cross with a 7-ton safety margin. The first vehicle across was a 2.5-ton supply truck at 1920 hours. The truck's passage tested the bridge's dynamic response to moving loads. The structure flexed slightly as the truck reached mid-span, the pontoons dipping perhaps 6 inches deeper in the water, then recovering as the truck continued toward the east bank. At 1945, the first Sherman tank crossed. Captain Robert Hayes of the 14th Tank Battalion later described the experience as unnerving but smooth. The bridge swayed perceptibly under the tank's weight, a slow oscillation that took approximately 4 seconds to complete a full cycle. This motion was expected and designed for. The pontoon spacing and cable anchoring created a structure that flexed under load but remained stable. Rigid structures would have fought the water's motion and eventually torn themselves apart. By 2100 hours, March 8th, 90 vehicles had crossed the Rhine at Remagen on the 51st Engineer Combat Battalion's pontoon bridge. The bridgehead was resupplied. Tanks that had been rationing ammunition suddenly had full loads. Infantry who'd been conserving rations received hot meals. Artillery batteries that had been limiting fire to conserve shells opened up with sustained barrages against German positions inland. The strategic impact extended far beyond the immediate bridgehead. German commanders who'd expected the Rhine to provide weeks of respite were watching American armor streaming across a bridge that intelligence said couldn't exist. The psychological effect on Wehrmacht morale was documented in prisoner interrogations conducted throughout late March. German soldiers repeatedly expressed variations of the same sentiment. If the Americans could bridge the Rhine in hours, nothing was going to stop them. The 51st's bridge at Remagen wasn't unique. Between March 7th and March 24th, 1945, American, British, and Canadian engineer battalions constructed 28 major bridges across the Rhine. The bridges used various combinations of Bailey panels, pontoons, and in some cases, captured German bridging equipment. Construction times ranged from 6 hours to 30 hours depending on river width, current speed, and enemy interference. At Oppenheim, American engineers completed a 360-foot heavy pontoon bridge in 24 hours on March 22nd. At WWII, British engineers built a Bailey bridge spanning 400 feet in 11 hours on March 24th. At Boppard, American engineers constructed a bridge under continuous artillery fire, losing 16 men killed during construction, and still completed the span in 18 hours. These construction speeds represented capabilities that simply didn't exist in military engineering before Bailey's design innovations and the systematic training programs that Allied forces had developed. The comparison to historical precedent was stark. Napoleon's engineers required 3 weeks to bridge the Rhine in 1796. Allied engineers in March 1945 were bridging the same river in less than 1 day. German military engineering hadn't stagnated during the war years. Wehrmacht pioneer units had their own rapid bridging systems, developed tactical bridging doctrine, and trained specialized crews. But German engineering was constrained by resources that had been depleted by 5 years of attritional warfare. By March 1945, German pioneer battalions were chronically short of equipment, fuel, and trained personnel. More fundamentally, German bridging doctrine was built around different assumptions. Wehrmacht engineers expected to bridge rivers during offensive operations when they controlled both banks and could work without enemy interference. Their equipment and training optimized for that scenario. Allied engineers, particularly by late 1944, expected to bridge rivers while under fire, with enemy observers watching from the far bank and artillery targeting the construction site. The doctrine and training reflected that reality. The Rhine crossings demonstrated how accumulated tactical experience could create systematic advantages that transformed strategic possibilities. Every bridge the Allies built during the campaigns of 1943 and 44 had refined procedures slightly. Every river crossing identified small improvements in anchor cable positioning, pontoon spacing, or traffic control. By March 1945, those incremental refinements had accumulated into construction capabilities that exceeded anything in prior military history. Donald Bailey's original design from April 1940 had been elegant in its simplicity. 5 years of combat experience had refined that elegance into a complete system where the bridges themselves were only one component. Equally important were the standardized procedures for site selection, the training programs that made construction crews interchangeable, the logistics systems that ensured components reached construction sites when needed, and the tactical doctrine that integrated rapid bridging into offensive planning. The modularity of Bailey components meant that bridges could be built to exact specifications required for specific situations without custom engineering. Need to cross a 200-foot river with 20-ton vehicles. Assemble 20 panels in single-height configuration with pontoons at 10-foot spacing. Need to cross the same river with 40-ton tanks. Use the same panels in double-height configuration with pontoons at 7-foot spacing. The components were identical. The configurations varied based on load requirements. This modularity extended to repairs. When German artillery damaged a pontoon bridge, engineers didn't need to rebuild the entire structure. They replaced the damaged section with spare panels and pontoons that were stockpiled precisely for this purpose. A bridge that took 8 hours to construct could be repaired in 30 minutes if only 1 or 2 sections were damaged. The repair capability changed the mathematics of artillery effectiveness. Before Bailey bridges, destroying a bridge meant the crossing was denied for days or weeks while engineers built a replacement. With Bailey bridges, destroying a section meant the crossing was delayed for less than an hour while engineers made repairs. German artillery would need to achieve multiple hits on multiple sections faster than engineers could repair them to permanently deny a crossing. That rate of fire exceeded what Wehrmacht artillery could sustain given ammunition shortages by late 1944. The industrial dimension of rapid bridging was as important as the engineering dimension. Bailey panels weren't sophisticated components that required specialized manufacturing. They were stamped steel parts that any factory with basic metalworking equipment could produce. Britain manufactured approximately 600,000 panels during the war. The United States produced similar quantities. Canada, Australia, and India also manufactured panels under license. This distributed production meant that supply was essentially unlimited. Engineer battalions in the field never faced situations where they couldn't build bridges because panels weren't available. The constraint was almost always tactical, whether the crossing site could be secured and defended, not logistical, whether equipment was available. The contrast with German capabilities was dramatic. Wehrmacht pioneer battalions by 1945 were often making do with improvised bridging materials because factory production of specialized equipment had been disrupted by Allied bombing. German engineers built bridges using whatever materials were available: timber cut from local forests, steel salvaged from destroyed buildings, pontoons improvised from fuel drums. These improvised bridges worked, but they took longer to construct and couldn't support heavy loads reliably. The Rhine crossings in March 1945 effectively ended Germany's ability to conduct coherent defensive operations. Once Allied forces established bridgeheads east of the river and maintained supply lines through pontoon bridges that couldn't be permanently destroyed, German forces in Western Germany were cut off from reinforcement or withdrawal routes. The result was the rapid collapse of Wehrmacht resistance throughout the Ruhr industrial region. The final bridge construction statistics from the European theatre documented the scale of Allied engineering efforts. Between June 6, 1944, D-Day, and May 8, 1945, VE Day, American, British, and Canadian engineers built or rebuilt approximately 7,000 bridges in France, Belgium, the Netherlands, and Germany. The figure includes everything from small Bailey bridges crossing streams to major pontoon bridges spanning rivers like the Rhine, the Seine, and the Meuse. 7,000 bridges in 11 months averages to roughly 20 bridges per day, every single day, for 11 consecutive months. The sustained construction rate reflected industrial-scale military engineering that treated bridge building as a routine logistical operation rather than a specialized engineering challenge. The human cost of that construction rate was documented but rarely emphasized in official histories. Engineer battalions suffered casualty rates approaching infantry rates when building bridges under fire. The 51st Engineer Combat Battalion lost 47 men killed and 189 wounded during March 1945 alone, the majority during bridge construction operations at Remagen and subsequent Rhine crossings. Combat engineers worked exposed positions while under direct observation by enemy forces. They couldn't take cover when artillery fire began because abandoning partially completed bridges meant the entire construction effort was wasted. The doctrine was to continue working unless fire became so accurate and sustained that casualties would prevent completion. This meant engineers often worked through artillery barrages, accepting casualties as the price of maintaining construction schedules. The psychological burden was immense. Engineers watched friends killed by artillery shells while standing 10 feet away, then continued working because the bridge had to be finished. The trauma was comparable to infantry combat, but occurred in situations where engineers couldn't fight back. Infantry under fire could return fire, call for artillery support, or maneuver to better positions. Engineers could only keep working and hope German gunners ran out of ammunition before the bridge was completed. Post-war studies of combat engineer veterans documented elevated rates of what we now call post-traumatic stress disorder compared to other military specialties. The combination of sustained danger, inability to defend oneself, and moral weight of knowing that delays cost lives created psychological injuries that persisted for decades. Yet the bridges were built. Every river crossing that military planners identified as necessary was bridged, usually within hours of being designated as a priority. The combination of Bailey's design genius, systematic training, industrial production capacity, and the courage of men willing to work under fire had transformed military engineering into something that previous generations would have considered impossible. The legacy of wartime rapid bridging extended far beyond 1945. The Korean War saw American engineers using the same Bailey panels and techniques that had worked at Remagen. The Vietnam War utilized evolved versions of the same modular bridging concepts. Modern military forces worldwide employ bridging systems that are direct descendants of Bailey's original design, updated with aluminum components and hydraulic positioning systems, but still based on the same fundamental principles. The civilian engineering world absorbed the lessons more gradually, but just as thoroughly. Post-war reconstruction in Europe relied heavily on Bailey bridges as temporary structures, while permanent replacements were designed and built. Some of those temporary Bailey bridges remained in daily civilian use for decades because they proved more durable and reliable than anyone expected. Modern disaster relief operations maintain stockpiles of modular bridging equipment, specifically for rapid deployment after earthquakes, floods, or infrastructure collapse. When natural disasters destroy bridges, relief organizations need to restore access within hours or days, not months. The equipment they use and the procedures they follow are direct applications of military bridging techniques developed between 1940 and 1945. The transformation of bridge construction from specialized craft to standardized industrial process represents one of the war's less celebrated but more significant technological achievements. Unlike radar, the atomic bomb, or jet aircraft, Bailey bridges didn't depend on cutting-edge physics or revolutionary new materials. They succeeded through systematic application of known engineering principles combined with manufacturing standardization and comprehensive training. This combination of modest innovation with systematic implementation created capabilities that changed strategic possibilities. Rivers stopped being obstacles that halted offensives. They became delays measured in hours. That transformation affected every military operation from Sicily in 1943 through the Rhine crossings in 1945 and continues affecting military planning in the 21st century. Donald Bailey died in 1985, having lived to see his bridge design adopted by military forces worldwide and used in civilian infrastructure projects across every continent. He never sought publicity, rarely gave interviews, and seemed almost embarrassed by the attention his design received. In a 1978 interview, one of the few he granted, Bailey said his goal had been simply to make the job easier for the soldiers who had to do the actual work. That modest description understated what he'd accomplished. By making bridge construction simple enough that soldiers with basic training could assemble structures capable of supporting heavy tanks, Bailey had changed warfare itself. The strategic flexibility that rapid bridging created affected campaign planning, tactical doctrine, and ultimately, the outcome of military operations throughout Europe and Asia. Lieutenant James Harper, who built that Bailey Bridge across the Volturno in September 1943, survived the war and returned to his pre-war career as a civil engineer in Yorkshire. In a letter written to his family in March 1946, recently archived at the Imperial War Museum, Harper reflected on his wartime service with characteristic British understatement. "We built 47 bridges during the Italian campaign. Rather satisfying to know that each one meant our lads could keep moving forward. Saved lives, I expect, though one can never be certain about such things." Harper's uncertainty about whether his work saved lives reflected the engineer's perspective. He saw bridges as technical problems requiring solutions. He couldn't observe the battles that didn't happen because German defensive lines were outflanked, or the casualties that were avoided because armoured support arrived hours earlier than German commanders expected. The strategic consequences of rapid bridging were invisible to the men actually building the bridges. But the consequences were real and measurable. Military historians analysing campaign timelines have calculated that rapid bridging capabilities accelerated Allied advances through Italy by approximately 6 weeks, compared to what would have been possible using pre-war bridging methods. 6 weeks in which German forces couldn't establish stable defensive lines, couldn't evacuate heavy equipment, and couldn't redeploy divisions to other threatened sectors. Similar analyses of the Northwest Europe campaign suggest that rapid Rhine bridging in March 1945 shortened the war in Europe by anywhere from 3 to 6 weeks. Those weeks translated directly into lives saved, both military and civilian. Every week that World War II in Europe continued cost approximately 100,000 lives across all combatants and affected civilian populations. Ending the war 6 weeks earlier saved roughly 500,000 lives. These calculations are necessarily speculative. History doesn't provide controlled experiments. But the correlation between engineering capabilities and operational tempo is documented across multiple campaigns. Armies that could bridge rivers rapidly maintained offensive momentum. Armies that couldn't bridge rivers rapidly stalled at water obstacles and gave defenders time to prepare. The Bailey Bridge's ultimate significance wasn't technical. The engineering was elegant, but not particularly complex. The significance was demonstrating how systematic standardization could create military capabilities that exceeded what specialized expertise could achieve. An army of adequately trained soldiers using standardized equipment could outperform an army of specialists using custom solutions. This principle extended beyond bridging. The same logic that made Bailey bridges effective made Liberty ships effective, made the M4 Sherman tank effective, and made countless other Allied systems effective despite often being technically inferior to Axis equivalents. Standardization enabled mass production. Mass production enabled overwhelming numerical superiority. Numerical superiority, combined with adequate performance, proved decisive. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.